Hello friends, welcome to a fresh new episode of our channel RG Innovations. If you have not subscribed already, please subscribe to our channel, click on the bell button and select all to get all future notifications of our video uploads. In today's video, we are going to discuss about a digital potentiometer, that is X9C103S, its detailed explanation, testing and interfacing with Arduino. We all know what a potentiometer is. Potentiometer is a device with three terminals. It is mainly used to change the voltage in a circuit. The symbol of the potentiometer, the symbol looks like this. There are three terminals. One is VH, that is voltage high. One is VL, that is voltage low. Another is VW, that is voltage wiper. You can change the resistance value by adjusting the position of the VW port between VH and VL, which is also called wiper position, and as a result the value of the voltage divided can be changed. Usually we see rotary type of potentiometer in which you can turn the knob to adjust the resistance. A digital potentiometer, often abbreviated as Digipot, is an electronic component that mimics the function of a traditional potentiometer but operates electronically, usually under digital control. It provides a variable resistance in a circuit, which can be adjusted by digital signals rather than the mechanical means. It's typically implemented with a resistive ladder, often an array of resistors, and an internal electronic wiper that selects the appropriate tap of the ladder. This is the general structure of a digital potentiometer. It is the VH or RH terminal, it is the VL or RL terminal, and this one is VW or RW terminal. And in this module there is control and memory, and we can control this module with these three pins, that is UD or up down pin, INC or increment pin, CS or chip select pin. Now if we see elaborately, this module internally looks similar to this. There is a 7-bit up down counter by which we can increment or decrement the value. There is a 7-bit non-volatile memory where it stores the current resistance, and another store and recall control circuitry which helps to store and recall the stored value. And here is 1 of 100 decoder. This decoder selects this resistance ladder and helps to change the value of this RW terminal. The value between the VL and VH terminal is always fixed. In the module today we are discussing, that is 103, it's a 10K. So the resistance between VL and VH here is 10K, and this RW or VW terminal changes with the digital signal that is provided here. Now few key features of a Digipot. It has digital control. Adjustment is done via digital input like serial peripheral interface SPI or inter-integrated circuit, that is I2C. Fine adjustment offers high precision with a specified number of discrete steps, each representing a specific resistance value. Automated control can be adjusted programmatically, allowing for automation and remote control. No mechanical wear. As it lacks moving mechanical parts, it doesn't suffer from wear and tear over time due to physical friction. Non-volatile memory in some cases. Some digital potentiometers can retain their resistance setting even after power cycling. Some common usage of a Digipot. Digital potentiometers are commonly used in applications that require automated adjustment or where physical access is limited, such as electronic calibration in measurement equipments, gain control in amplifiers and signal conditioning circuits, adjustable power supply outputs, automated system where resistance needs to be changed based on different conditions, remote operated volume control, etc. So all these are in general details of a digital potentiometer. Now we will look into X9C103S digital potentiometer that we are going to discuss today. This is how the module looks like. Here is a chip VDPC103. This is the potentiometer chip, and this way here are three terminals. One is VH, one is VL and one is VW. Just like a normal potentiometer, VH is the voltage high terminal, VL is the voltage low terminal, and VW is the voltage wiper terminal. You can see the schematic given here. And this way here are 5 terminals. One is VCC, that is the power supply, CS is the chip select, INC is the increment, UD that is up or down, and the ground that is the negative power supply. This is the back side of the module. Here it says VCC 3 volt to 5 volt, VH 0 volt to 5 volt, and VL minus 5 volt to 0 volt. Although it's written 3 volt in VCC, it does not properly operate in 3 volt. It works perfectly from 3.3 volt or 3.7 volts. So I would suggest you use 5 volt for this module. Now some specific features of this X9C103S module. It has 100 position settings. The X9C103S has 100 discrete resistance steps, allowing for fine adjustments of the wiper position. 10 kilo ohm total resistance. The specific model has a total resistance of 10,000 ohms or 10 kilo ohms. Digital control interface. The device is controlled by 3 digital inputs: increment, chip select and up down. This makes it compatible with common microcontrollers like Arduino or Raspberry Pi. Non-volatile memory. The X9C103S retains its wiper position even after power is removed. This is achieved through an internal mechanism that stores the position when the chip is deselected. Low supply voltage. This module operates with a supply voltage range of 3.3 volt to 5 volt, making it suitable for various applications. Small package. It is typically available in an 8-pin SOIC package, making it easy to integrate into compact circuits. Wiper tolerance and stability. The wiper's resistance changes by a predictable amount with each increment or decrement, providing stable and consistent control. Now some specifications of X9C103S. Supply voltage. This is the voltage range within which the X9C103S operates reliably. The typical range is between 3.3 and 5 volt. This flexibility makes it suitable for various applications and compatible with a wide range of electronic systems. We mentioned it earlier. Now the supply current. This is the current consumed by the device during operation. The typical current draw is about 3 microampere in standby mode and up to 3 milliampere when actively changing the wiper position. Wiper current. It is the maximum current that can flow through its wiper. It's typically rated about 1 milliampere, indicating that the wiper is not intended for high current applications. Practically, we have found that 4 milliampere is okay through the voltage wiper terminal. VH and VL. The VH and VL terminals of the X9C103 are equivalent to the fixed terminals of a mechanical potentiometer. The minimum voltage is -5 and the maximum is +5. Now how to switch the potentiometer for incrementing, decrementing or storing the wiper positions. First, for moving the wiper in the upper direction, the increment pin should be toggled low while CS and UD is low and high respectively. That is, the wiper position moves at the falling edge of increment pin. Moving the wiper position in the upper direction means incrementing the counter, resulting in RH to RW decrease and RL to RW increase. Second, for moving the wiper in the lower direction, the increment pin should be toggled low while CS and UD are both being held low. Lowering the wiper result in an increment of RH to RW and decrement of RL to RW. Finally, when CS rises high while the increment is high, the current wiper position at the rising edge of chip select is stored as non-volatile memory. The stored wiper value is very useful because it is retained even when the power is turned off and on. Now let us come to the practical explanation of the Digipot module. We have connected the Digipot module with an Arduino to give the demonstration. In the Arduino Sketch, we have written 4 functions. One is for decrementing the value, one is for incrementing the value, one is for storing the wiper position in the memory, and one is for reading the wiper value and display it. We have used 3 buttons here. First button will decrease the value, second button will increase the value, and the third button will show the current VW position or the wiper position. So for this, we have connected the first button with the digital pin 2, second button with the digital pin 3, and third button with the digital pin 4. And here this module we have connected the ground pin, the power supply ground pin with the ground pin, the VCC pin with the digital pin 12 of the Arduino. We could have connected the VCC pin with the 5 volt pin of the Arduino, but that creates a problem while saving the memory or restarting the module. It resets the memory of the Digipot module. So we are using the digital pin 12 to give the power supply. The CS pin is connected with the digital pin 9, the increment pin is connected with digital pin 8 and the up down pin is connected with digital pin 7, and we have connected the volt wiper terminal with the analog pin 0 and voltage high pin with the 5 volt of the Arduino and voltage low with the ground pin. And these three are the 10k pull down resistances we have used with the switch. So this is the circuit. Now we'll move on to the practical demonstration. So let us first discuss about the Arduino Sketch that we are going to load onto the Arduino, which will execute the code to control the Digipot, and then we will come to the testing part. So here is our Arduino Sketch. At the beginning we have taken some constants, that is UD pin to 7, increment pin to 8, CS pin to 9 and a VCC pin to 12, and one analog pin, that is RW pin or the VW pin, wiper pin to A0. Two more constants we have taken, that is increment delay and CS delay. We need to give some delay after the increment pulse and the chip select pulse, otherwise these operations will not perform properly. So then in the setup section we have initiated the serial communication, and then we are defining the pin modes, that UD pin to output, increment pin to output, CS pin to output, VCC pin to output and RW pin to input. Now initially we are setting the increment pin to high, then giving some increment delay, and then we are setting the CS pin to high also, the chip select pin, so that the chip gets deselected, then giving some delay, chip select delay. Now we are giving power supply to the Digipot module. If the Digipot module is given power previously, then in this section, transition sections, it clears the memory. So we have given the powers in the increment pin and CS pin, and then we have given power to the VCC pin. Now we are printing in the serial that setup is complete. Now this is our first function, that is increment resistance and number of steps. As we said, there are 100 steps in this X9C103 module. So how many steps we are going to increase, that we have to mention in this function. So first, this function increments that much steps in the for loop, and then after incrementing we are turning the CS pin to high to save the current value to the memory, and then we are printing in the serial monitor increment resistance by number of steps. Then the opposite function, decrement resistance, it is also same. We are taking an input of the number of steps, and in the for loop we are decrementing the given number of steps, and then we are saving the decremented value to the memory. Now we have written a separate function for save to memory. This function saves the current VW value to the memory, but we have not used this function in the program because already in the increment and decrement function the save to memory is done. And one more function, that is read resistance. By this function we are reading the resistance from the VW pin. So here we are reading the analog value in the A0 and then printing it in the serial monitor, the analog value. Our setup, our function declaration is complete. Now we are coming to the loop section. First we have given a while loop so that the program code does not start executing before the serial monitor is open. And now we have given 3 if statements. In the first statement, if digital pin 3 is high, then it will increment resistance. If digital pin 2 is high, then it will decrease the resistance by 1 step. And if digital pin 4 is high, it will read the resistance of the VW port. And our code is complete. So this is very simple code. At the beginning we will not test it through the A0 port. First we will test in the multimeter that whether the resistance is increasing or decreasing or not. After that we will see it in the serial monitor how the value of the resistance is changing. So now we will connect the Arduino to the computer and we will upload the sketch. So this is the circuit that we have built, but we have not yet fixed the Digipot module here. This is the Digipot module. We have added header pins here to fit it on the breadboard, and in this module there is some extra space at these two sides. At both the ends some extra space is there. So in another module we have trimmed it off. It is the same module, but we have trimmed off the ends. So first we will put it on the breadboard and connect it with a multimeter and upload the Arduino Sketch. So the module is fixed on the breadboard. We have already seen the circuit. This is the same circuit here we have built. These are the 3 switches. This one works for decrement, this one works for increment, and this one shows the current wiper value. But in case of the multimeter it will not work. We will only check with increment and decrement, because memory read cannot be shown on a multimeter. When we will show it on the serial monitor, we will show that how the read function, the read memory function works. So first connect it with the computer. The Arduino got power, the Digipot module got power. Now we will upload the Arduino Sketch. First selecting all the appropriate options and then clicking on the upload button. Uploading done. So now getting back to the circuitry. I am zooming out a little to fit the multimeter on the screen. I have connected two crocodile clips with the VL pin and the VW pin to see the increment and decrement of the resistance. So here is the circuit, here is the multimeter. I am turning it on. If you can see, the multimeter set at 20K. Now I will connect the crocodile clips with the probes. So currently the resistance is 7 kilo ohms. Now we will show how it is incrementing and decrementing. So this is the decrement button, this is the increment button. Now we are decrementing it. See, it's decrementing. And if I press this button, it will increment. It's increasing or decreasing one step. That means approximately 100 ohms. This button does not have any function right now. Now how to check if the resistance is stored in the memory? So we are removing the power now. Now it has infinite resistance. We are connecting the power back. See, it has come to the same resistance. So even after removing the power, it is retaining the resistance. With this module, I have found one problem. The maximum value, although it is said to be 10 kilo ohms, I have kept the button pressed. The maximum value that this module gives is 8.5 kilo ohms. It does not increase anymore. And if I keep it pressing down, let's see what is the minimum resistance. So the lowest resistance is almost 0. Now I have another same module I have shown you. Now I will replace this module with this module. So removing this one and inserting this one. So as soon as I inserted, see, the last status of the wiper is loaded. Now if I increase this, let's see how far it goes. Again, this module has almost 11 kilo ohms of resistance. So even if the name says it is 10 kilo ohms, one of the module is giving 8.5 kilo ohms and another module is giving 11 kilo ohms. So before you use any of these modules into your project, please check what value is it. So in the multimeter, we have shown the increment and decrement of the resistance. Now we will see what happens in the serial monitor. Because after all, this module is going to be used for automation, so we need to read the value onto Arduino or any other microcontroller. In our case, we are testing it with an Arduino Nano, so we will remove these two wires. But since there is some extra space here, first let us remove the multimeter from here. Let's zoom in. As this module has some extra PCB at both the ends, inserting the wires is a little bit troublesome. So once we are removing the module, then removing these two wires, the crocodile clips actually, and we will connect the, now we will connect the VH pin with the positive power supply and then the VW pin with the analog 0 pin, and we are inserting this potentiometer. We can zoom in a little more. Now we will see what happens in the serial monitor when we press these buttons. We will see it side by side. So let's split the screen into two halves. So we have splitted the screen half. Now first we will remove the power, then connecting the power. It shows setup complete. First let us see what is the current value into the memory. It's 1023. You remember we have increased this value to the maximum when we checked in the multimeter. So it's showing the highest resistance 1023. Now we will decrease it. one step, one step, one step, one step, one step, 5 steps decreased. Let's see what is the value. It's now 972. Now few more steps I am decreasing. It's 857. Few more steps I have decreased. Now it's 724. Now we will see the increment button. So you see it's increasing with this button and decreasing with this button, and it can recall the memory what is stored into the Digipot. Now again I will show you by removing the power. So this is the module. I am removing the power. See, as soon as I remove the power, it shows not connected. The Arduino has been removed. Now I am connecting. Now I am clearing the serial port, connecting the Arduino. Setup is complete. Now we will see what is stored in the memory. You can see the last value is recalled from the memory. Increasing one step, decreasing one step. So this is how our Digipot module X9C103S works. Hope I am able to make you understand everything clearly. If you have any confusion, please feel free to ask me in the comments. I'll definitely try to clear your confusion. So I am concluding here today. Hope you liked the video, and if you like the video, please hit the like button and do not forget to subscribe to my channel RG Innovations. We will meet again in a new video. Till then, bye bye, take care, have a nice time. Thank you.